Hi everyone! So today I'm going to be talking to you about equivalence classes. So as you probably guessed, they do have to do with equivalence relations, but they also have to do with something called a partition. And so just in case you've never heard of what a partition is, which I'm pretty sure you haven't, probably. I don't really know the curriculum of all the classes at MSU very well though, so what do I know? Okay. So let's define it. So whenever you take a partition, it's of a set, okay? Of a set X is a collection. If you go on into analysis, often they take partition of a interval or something like that. But an interval is a set. So, okay, so it's a collection of sets. Maybe let's call them X sub I, such that X sub I intersected with X sub J is the empty set whenever I doesn't equal J. So my index that I'm over is probably just going to be like 1, 2, 3, 4, Okay. And when we union over all of our indices, we get our set back. Okay? All right. So let's break it down a little bit because there's a lot kind of going on here. All right, so when we do this, when we say the intersection of xi and xj is the empty set whenever I is not equal to j, what we're saying here is we're getting distinct elements, or getting distinct sets with no overlap, okay? And then here, what we're doing here is we're making sure we get all the elements. We get everything. We catch everything. Okay? So we're not like, oh, we took a partition, but we left out a bunch of those elements. Like, we don't care about those elements. No. If those elements are in the set X, then they need to be in some of the sets of the partition. Okay? But in such a way that no two partitions have any of the same elements. No two of the sets in the collection, that is the partition, has the same elements. Okay? So if you have x1 and I have x2, we have none of the same elements as each other. Okay? But if you, me, and whoever else has all the other xi's, if we all pool them all together, so none of us have the same elements with each other, none of us. There's, is it go fish, but if we pool them all together, all of our sets, if we take all of our bowls with our elements in it, and we dump them all into one big bowl, that's X. Okay, so we have all the elements, but we all have different elements. Okay? All right, so let's make a note that it's not necessarily a finite collection. So I don't think that this is of huge importance, at least right now, with what we're going to do with them. Well, actually, it might, because I remember in the past there was a homework question where we were looking for an infinite partition. But really all they needed to do then was like figure out what the pattern was and talk about what the pattern is. So like, I think it was like every element only twiddled itself or something. So, but we had an infinite number of elements. So what you would do is you would say, okay, for every element gets its own set in the partition. So that's why you can index over different stuff. All right. Okay, if that was confusing, that's okay. Like this is confusing stuff, but we will get there. I'll go through the definition of equivalence classes, which has to do with partitions, and then in the next video I'll be doing examples of equivalence relations and their classes. Okay? All right. Moving on. If twiddle is an equivalence relation on a set X, then and only then, meaning if you just had a relation and it was an equivalence relation, this is not true. So if twiddle is an equivalence relation on a set X, then and only then can we define equivalence classes on X? Okay. All right, so I haven't necessarily defined them yet, but this is our first time seeing it. Okay. The equivalence classes, equivalence class of an element little x in our set X is, and so now here's how we denote it, okay? We're going to put these brackets around X, and that's it, okay? But what does this define? Well, it's going to define a set, okay, of all the elements Y in our set X such that X twiddles Y. All right, so some of you might be thinking, and rightfully so, okay, well, why the heck is it X twiddles Y and not Y twiddles X, or X twiddles Y, or Y twiddles X? Well, since twiddle is an equivalence relation, X twiddles Y, and if X twiddles Y, if X twiddles Y, then Y twiddles X, and if Y twiddles X, then X twiddles Y, which means in general that it doesn't really matter what order we put them in anymore, okay? All that matters is, do they twiddle each other or do they not twiddle each other, okay? Because if X twiddles Y, then Y twiddles X. If Y twiddles X, then X twiddles Y, okay? But if X does not twiddle Y, then Y does not twiddle Y. I'm sorry, no, that's incorrect. Y does always twiddle itself because it's equivalence relation. If X does not twiddle Y, then it cannot be true that Y twiddles X, because if Y twiddles X, then X twiddles Y. Okay, so all we need to know is, do they or do they not? Do they twiddle each other or do they not twiddle each other? Okay, because it's one or the other, all right? I hope that made some sense. All right, but this kind of goes to show you how powerful equivalence relations are. Well, maybe it does, hopefully. All right. When talking about equivalence classes, okay. So when talking about the equivalence classes of twiddle on X, we want a partition of X. So this kind of makes sense because we don't want to talk about so let's say 1 twiddles 2 here, then 2 twiddles 1, okay? So then 2 is going to be an element of this. 1 and 2 are both, and then 1 and 2 are also going to be equivalence classes in the equivalence class of 2. Right? So if these were the same thing, well, I don't want to list a bunch of the same thing, okay? I mean, this is just a quick and messy example, okay? So we would like a partition, okay? We want to get all the elements, but we don't want any repeats, okay? So we need to figure out a nice way, and this is a fun proof that you can probably do on your own, is prove why we can always get a partition when we have equivalence relation. So when we don't have an equivalence relation, we can't always get a partition of equivalence of classes. Okay? All right, this is fun. If you just have a relation, if like one of the things isn't true. Okay, so let's move on. So find some tiny xi's in our set X such that, well, kind of the stuff we were talking about before. Not kind of, but exactly what we were talking about before. So the class of xi intersects with the class of xj equals the empty set when I does not equal j, and the union over all the i's of the classes of xi equals our set X. Okay? So we're not looking at every single element in X. We might be, but that's not necessary, okay? Maybe the whole set X is an equivalence class. So maybe all you need is one element from it, and then you're done. Maybe it has 2 equivalence classes, so you need to find 2 elements, an xi and an xj. Okay? All right. Well, I think that's where I'm going to end it. Well, okay. So here we go. How about this? Example. X is the set 1, 2, and 3. Now the set of ordered pairs 1, 1, 2, 2, 3, 3, 1, 2, 2, 1 defines an equivalence relation twiddle on X. Okay, and you could double check me on that. What are its equivalence classes? Okay, so let's figure out what they are. Well, let's maybe start with the equivalence class of 1. So consider, all right, well that's going to be all the elements in our set X such that 1 twiddles. Okay, so that's going to be, well, it twiddles itself. Okay. And then also, oh, okay, here it says it twiddles too. All right. Well, since it's so small, we could consider all the classes and then determine if any of them are equal to each other. Okay. So let's look at 2 and 3. Okay, but it's the same kind of deal. So 2 twiddles itself up and 2 twiddles 1. Okay. How about 3? Well, 3 only twiddles itself, and that's totally fine. Okay, so the equivalence class of 1 is equal to the equivalence class of 2. Okay, so maybe let's choose 1. Consider 1 intersected with 3 is the empty set. Okay, and those are the only 2 classes that we have to check that their intersection is 0, or is the empty set. All right, well, how about them union together? Well, that's going to be 1, 2, 3. Oh, that is X. Okay, therefore, our equivalence classes are, and if you pick 2 instead of 1, that's fine. But we can't have both 1 and 2, okay, because their intersection is not going to be the empty set. All right, so now we're all done. Okay, next video, I will have a lot of examples. Okay, that's going to be the whole video. It's just examples. So make sure you watch that too. Have a good one. Bye.